In this little portion, we will talk about the synthesis of organohalides, and a big part of the synthesis is free radical reactions, which is how you actually synthesize the organohalides. So let's review some of the synthesis that we have already done for alkyl halides, and we synthesized haloalkanes from alkenes, okay, where we did the hydrohalogenation of an alkene, and we did the Markovnikov's addition, where we have the hydrogen going to the carbon with more hydrogen, and the Cl or the chlorine or the halide, whatever it is, it's adding on to the carbon with less hydrogens. Okay, so the Markovnikov addition, we did that. And then we've also done halogenation. This was hydrohalogenation, just halogenation. And in case of halogenation, you will add a 1 molecule of halide, and that 1 molecule will be a 1,2 addition, okay, or a vicinal addition. And the addition is also an anti-addition, if you remember, because one chlorine goes on one side, the other one should go on the other side. In this case, it doesn't matter because it's not stereochemical reaction, but if there was stereochemical centers possible, then if there were stereo centers, then you would see the anti-addition, okay? But that was the mechanism of the reaction. So those two syntheses are from alkene. And then we also did the synthesis of haloalkanes from alkynes. We never really called it that way. We just called it a reaction of alkyne, but hydrohalogenation of alkynes give us haloalkanes. The hydrohalogenation of alkynes is Markovnikov addition, okay, which means that the hydrogen will go to the carbon with more hydrogen. So if we take an alkyne, which is asymmetric or terminal, then the hydrogen will go to the carbon with more hydrogen. That's 1 mole. In the second one, it's the same thing. So you end up getting all the hydrogens on the terminal carbon, and then on the internal carbon, you will get the bromines. This bromines, the relationship here is geminal. And then you can also add halogens to alkanes. And once you add the halogens, first of all, you add 2 moles, just like you added 2 moles of HBr here. You will add 2 moles of the halogen also. And whatever you add, then you will end up getting 4 atoms of that halogen. So whether it's chlorine or bromine. Now remember, we don't usually form the fluoro and the iodo compounds, okay, using these methods. And you can also make alkyl halides from alkanes. So this is all free radical because alkanes don't really have a functional group. The only thing they do is combust, which is burn in oxygen. So we really didn't do any reactions for alkanes because there isn't one until we get to free radical reactions. And so free radical reaction is a substitution reaction that we do on alkanes. So the mechanism is free radical, which we've already done. So you take methane, you take any kind of halogen, chlorine, bromine. Remember always that bromine is a little bit more specific than chlorine. Chlorine will halogenate at multiple locations, whereas bromine only at certain positions. And so you do substitution reactions, and this is the only way substitution will work on any kind of an alkane. Otherwise, alkanes have such bad leaving groups that it's never going to work, okay, for an alkane. So let me just give you a little idea about the specificity that I'm talking about for a bromine. So for example, if you have something like this and you treat that with bromine in presence of light and all that, so it's a free radical reaction, the major product that you're going to get is this one, right? Because this carbon is going to give you the more stable radical. But if you were to do the same reaction with chlorine in free radical mechanism, then you can get chlorine anywhere. Okay, so it just doesn't have to be here. It could be here, 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 everywhere. You would get chlorine. I'm not going to write all the products, but you get all these constitutional isomers if you were to treat with chlorine. So bromine is just a little bit more specific and better to work with, okay, for free radical reactions. Some of the other reactions that you need to know regarding the free radical reaction, and this is on alkenes. So we've talked about addition reactions on alkenes, but that was just a normal kind of addition reactions that you get from alkenes. So here I'm just going to mention a couple alkene reactions, addition reactions, and some substitution also that you can do with alkenes in free radical mechanism, which give us just a little bit different kind of a product. So for example, right here, if you take a terminal alkene, now remember, if you have a symmetric alkene, then whether you do free radical or normal kind of addition, it's not going to matter. So this is only when you have a terminal alkene or an asymmetric alkene. So normally if you add HBr to this, you will get Markovnikov addition, which is that hydrogen goes to the carbon with more hydrogens. That is Markovnikov. So this is what you have learned so far. But here is what happens when you treat an asymmetric alkene in presence of peroxides, or as we say free radical mechanism, is that you get bromine on the carbon that has more hydrogen. So it is reversed then, okay? The addition is reversed, and that's anti-Markovnikov. And this is something that we have already covered in case of mechanisms in alkenes. So you may want to go back and look at that and see how this works, okay? But otherwise, for alkene addition reaction with HBr, you get anti-Markovnikov. So then there is also the allylic substitution on an alkene. So again, let me remind you, if you take an alkene and you add bromine to it, you will get a vicinal dibromination. So whether it's symmetric or asymmetric, it doesn't really matter. You will get the vicinal addition, you will get the syn addition, all those kind of things that you know about. So that's the normal kind of addition. However, if you take bromine with peroxide, so which means free radical reactions, so now you get a substitution on the allylic position. So it's not even an addition reaction. The alkene is still there. It's a substitution, because now what you have done on position number 3, which is the allylic position, so 1, 2, 3, the third position from the double bond, that allylic position has 2 hydrogens, right? So now 1 is substituted with bromine, okay? And so this is allylic substitution, and this is what happens when you add bromine. So bromine does not add like vicinal bromines in a normal alkene addition reaction, okay? So in the case of peroxides, or in case of light in presence of bromine, which changes the mechanism, and so in that mechanism you ended having allylic substitution. Again, the mechanism is covered when we did the free radical reaction, so you may want to go and look into that. This is just a review of how many different ways you can get alkyl halides, and the different mechanisms and the different products, okay? So you can make a list yourself also. So this again, this is just another example. So I've shown you here, this is the alkene, and this is 1, 2, 3rd position here, 1, 2, 3rd position here. Either position is equal to each other, okay, when you do bromination, but the thing is that you can actually do free radical and get allylic substitution. I'm also introducing this reagent here for you, and bromosuccinimide, NBS, which works only by free radical mechanism, okay? So if you see NBS anywhere, that is telling you it's a free radical mechanism, and you should be doing allylic substitution at this point. So in this little presentation, you learned about how to make different alkyl halides, starting from alkene, alkynes, and alkanes, and then of course the allylic, allylic, I don't know, alkenes, you know, sort of. So in any case, all the different kinds of alkyl halide synthesis, make sure you make a list for yourself. And then we did the one new reagent, which is the NBS.